Stream now. So I'll get started in a moment here. Awesome. Well, thanks everyone for joining us. Today we're going to talk about serving the different types of features. The term real time gets thrown around a lot, and I want to really explain what that means and how to think about it from a machine learning context, especially in relation to your data. So without further ado, let me share my screen. So the agenda today, so this is the batch streaming real-time feature webinar. If that's not what you're looking for, you are in the wrong place. But if it is, I will do everything I can to go through this agenda. We're going to break down feature stores generally. We're going to really break down the problem space, like what is the problem that feature stores aim to do. We're going to have a demo, so we'll show some code to really kind of explain the different types of features. And then I'm also going to get into and cut into LLMs, AI, etc. We're scheduled for an hour. I think this one will probably be close to like 45 minutes. I will leave a little bit of time for Q&A at the end, though. So this is me. There's like 3 pictures of me now on the screen. And I'm the founder and CEO here at Featureform. Featureform is a way for data science teams, ML teams to define, manage, and serve their model features. So all those times where you have those untitled notebooks, you're copy and pasting transformations between things, you don't have features in production, you're not monitoring them for drift, all that kind of the problem space that exists around the data part of machine learning is what we aim to solve. I built Featureform at my last company. My last company, we were doing recommender systems for over 100 million monthly active users. We were processing, predicting subscription, predicting churn, doing recommendations. And we found that feature engineering was one of our core ways to make our model more performant and more reliable. And the process to do that was a mess, to say the least. Cool. So obviously, to use a model, you have to train it. Once it's trained, you're going to use it in production. So let's talk about that part. So the way we typically will create a feature is, as a data scientist, we'll work in our notebooks. We will interact with our data infrastructure. Could just be locally with a file. We'll build a set of transformations that eventually end up in a feature set. So a set of inputs to a model. A feature from our perspective is just any input that goes into a model. And we'll then use that along with a label to train our model in a supervised context. So this is kind of the process of building features. Now, what does it mean to put a model in production? I'm going to break that down to, there's 2 types of models, production models. There are interactive models and batch models. Interactive models are models such that interact on a request time basis. What that means is they're kind of always alive, like always there, and then you can hit them with requests at any point. That would be an interactive model. The other type of model, which we won't talk about as much today, but are very interesting and have our own set of problems, are batch models. You can think of this as a model that runs every 24 hours. Maybe it scores all your leads, or it generates the personalization for all the emails that go out tomorrow. Those sorts of models are typically set up to run on a clock. They're not typically always running. They kind of come up, do all of our predictions, go away. And for today, I'm going to be speaking much more on the interactive model case. So I'm calling it an interactive model. Is an interactive model real time? I don't know. I don't know what real time means. And so we'll talk about that later, of what the components, because people call a lot of different things real time. So I'll talk about and break down the three things that people call real time. Interactive models are super common. Literally as a consumer, any product interactive where you can see the machine learning that's an interactive model. So every recommender system is typically going to be an interactive model. They can be run in batch. In theory, you can like pre-cache recommendations, but more often than not, they're interactive. Fraud is often an interactive model, especially if it's like with every transaction. Chatbots are almost by design have to be interactive. Interactive models have some specific problems that exist for them that don't exist as much for batch models. One is maintaining uptime. The model is always there and always has to be ready to accept requests. So there's this problem space of how do I deploy and make sure this model is constantly running. It gets harder as you think about updating it and doing other stuff, but I'm going to not get into that too much. Typically there is a latency budget. It depends on the model. Like if you are dealing with a consumer, like if you're an ad tech company, like that latency budget is super low and very, very, very strict. Whereas, if you're doing near real-time fraud or something, you might be able to get away with like a second or two even. And in those situations, it's not, as hard from the model's perspective to get there. The other thing is because the model's always up, there is a temporal component that doesn't exist as much with batch models. Batch models just like exist in the world and go away in a short enough time frame that the world doesn't change. But if you're like building a recommender system, like people's tastes are constantly changing in production, and you can't just train every 5 minutes. So you do need to be able to capture and see and think about how the underlying features are changing in production. So those are the core things that make an interactive model different. So how do we solve this? Well, there's a trick to make things typically have higher uptime, be much faster. It's caching. So boom, we can just cache it, right? Like we'll just have something like Featureform run our job on Databricks against our data and cache the pre-processed features, the inputs to the models in something like Redis, which in this context, Featureform, we'd call an inference store. Some people would call an online store. So there, problem solved. We can all go home now, right? Because this is going to maintain a certain amount of uptime, assuming you can keep your caching layer up, which is probably, is doable. Latency, much easier to serve a low latency when things are cached for obvious reasons. Monitoring for drift, Featureform does that automatically. So if you do this, you kind of already get that. So we've solved it, right? Well, not quite. Caching comes with its own problems. How often do we materialize that cache? We have to update the cache. Like how often do we do that? Can everything actually be pre-processed? Some things can't. Some things come at request time and they can't be like, you only know what the data is at the time of the request. So you can't really cache it. What's the cost of pre-processing it? Like if you're only going to serve features very seldomly, but you also have a giant data set, it's probably really wasteful to pre-process every feature, especially for expensive features. For example, if you're going to like use ChatGPT to generate a summary of everyone's last blog post, and you have 100 million users, like that might take a year to run 100 million requests like that. So it can't be done. And, caching, like there's a lot of other issues of caching or things you might want to think about, like, hey, like, how about if our entity set keeps growing, do we need to think about things like TTLs? Like there's all kinds of other nuance to getting this to work well. So I want to really highlight that how often do we materialize the cache? Like, some features, they don't change that often. For example, the average price that a user spends in the last year on items. Like that doesn't change that often. The user's like income in the last 90 days, like it's probably going to stay relatively steady. In those situations, like materializing every 2 seconds is wasteful. You can probably get away with like every day, if not even less. And with other things every hour. So what I'm getting at is like the thing to think about is how fresh do we need the feature to be? And the way to think about that is, well, how often does this feature value really change? If it's relatively static, then you can get away materializing less, which means that it just makes things easier, it's cheaper, it's more efficient. And at the same time, there are some things where you need to materialize them more. Now, on the extreme, there are features that are changing constantly. A very simple example would be, what is the last song a user listened to on your app, like your Spotify, let's say. That's changing literally every time a user does anything. In that situation, you really want freshness to be as close to like right now as possible. And so we enter the wonderful world of streaming. Streaming sucks. It's not something that I would recommend people just do just for fun. It's quite painful. Typically, there's a lot of things. If you've ever used like something like Flink, you would quickly see how much nuance there is to get streaming to work correctly, how many things you need to think about, like what's a watermark, like what does exactly one semantics mean, like all these things start to come up that just you don't have to think about in the batch context. Now the benefit obviously is that you will be very, very close to very fresh data. The con is you're adding a lot more complexity into the pipeline, but you can mix them. Some companies will say, hey, like everything should be streaming. Like some feature store companies have taken that approach with their messaging, and I don't buy that. I think it adds a lot. It will always add a level of complexity, and some features benefit from being streaming. So the complexity is well worth the trade-off of the reward, the how well your model does, how good it can perform. In a lot of cases, it's not. It's as much easier to keep things in the batch context. So now we have two types of features. We have batch features, we have streaming features. We use streaming features when data is, or the feature values are changing very rapidly, and having the most fresh data is very valuable to the model. On the batch side, that's going to be for data that typically doesn't have to be as fresh. And we can decide, I mean, that's a spectrum. So you can decide how often you want to materialize the feature. It could be every hour, it could be every 5 minutes, it could be every day, it could be every week, it could be every year. Is streaming real time? I don't know. Again, real time is kind of being used in a lot of different contexts. I would frame it as there's a real time perspective of freshness, which is like how recently was this data processed in that situation with a feature. When you think of feature freshness, it's like how up to date is this feature value? And then there's latency. So it's almost like on one end, before it gets to the cache, what's the freshness? And then on the other end, it's a latency, which is like, hey, I'm serving for this feature. My model has to make a prediction within 50 milliseconds. How many of those milliseconds do I spend waiting for the feature value to get to the model? So I would frame those as two different things. And then the final piece of it is the uptime. Like for real time, like when people say it, sometimes like, oh, this model is real time. Sometimes they are using like all batch features, so relatively stale features. They might actually be not in a situation like a recommender system where they have like a really, really low latency requirement. And typically what they mean there is that it's an interactive model, which just means it's always up and it's always ready to accept requests. So these are kind of the three things that people talk about when they say real time. So I think it's important, like when someone tells me we need a real-time model or real-time features, I try to break down, well, what does that mean? And it's usually one of these three things that they care about. Sometimes it's all three, but oftentimes it's only a couple, or it depends on the context. I mentioned earlier that how about in situations where the feature can't be pre-processed? For example, you can't pre-process a feature that's dependent on the chatbot's last message because by design, you don't know what that message is going to be until the request comes in. An incoming transaction for fraud, same thing. A computer vision model that predicts if a picture has a bird in it, you can't pre-process like a black and white image of an image you don't have yet because you don't have it yet. So there are a set of features that have to be processed at the time of their request. So request time features, sometimes called on-demand features. And those actually would have to happen after the inference store. Sometimes on-demand features can actually use pre-processed features. For example, you might pre-process the average number of songs a user listens to across your whole application, but your on-demand feature might be the delta between this users and the average, and you might want to have that really, really up to date, and so you might set up an on-demand feature. So these are the three types of features: streaming, batch, on-demand. The decision tree of whether you need to be on one side inference store and the other is should I cache this feature value? And that's going to depend on the latency you have, if it's even possible to cache it. And sometimes there's some things that are on cost of like, how does it really make sense for me to pre-process everything, etc. Now, on the pre-processing side, there's a decision between streaming and batch, and that's going to depend heavily on how much complexity are we willing to take on to get the data, the features to be as fresh as possible. If you're batch, then you can get away with, let's call it 5 minutes of staleness in the data. With streaming, like you might need it up to at least up to the second, if not even less. Great. We're done, right? Like we just serve features like this. Well, unfortunately, serving features in production is only half the game here. The other half is training the model. There's typically a fence, as you can see in this image, between training and production. So people will build a pipeline, like in your experimentation phase, when you're building your models, coming up with features, you're working typically in like notebooks. And there's a gap and typically a whole different process to build your features in training and like come up and experiment and have that working notebook of a model in it. And then getting in production, you kind of, it depends on the company. Different companies do it differently. Some companies literally throw it over the fence to another team to go implement it. Some companies, the same data scientists, when they're there, they have to go and they have to kind of put on their like ML engineer hat, and they have to go and figure out how to process streaming data to get that feature in production. So there's this huge disconnect between training and inference pipelines. And the root problems of those, the causes of it is kind of everything we talked about, like the inference and real-time production features have a whole different set of things you need to think about. And the things that you need to think about there add a lot of complexity, which makes things move slower, which is fine in production. But when you're experimenting, you kind of want to move as fast as possible. You don't want to worry about streaming semantics when you're just coming up with what features you want to build. And so that's where the disconnect comes in. And then in terms of what that disconnect causes, one is a ton of wasted time. Two, it's very error prone. Like it's almost like, imagine if you're maybe have a software engineer background, like imagine it's like, hey, when I'm writing my tests and writing my new feature or new software, I write it in Java. And then when I actually deploy it, I actually take my Java code and rewrite it to Go. It just would be like such a silly idea because like you might do things wrong. It's just some things that work in Java don't really work very well in Go or are really awkward. So it's almost, why would you speak two different languages? Like what you want is something that can speak both languages. So that's actually one of the core. Oh, and I should add another meme for y'all. It is also very frustrating because we spend more of our time experimenting on and coming up with new features than we do deploying features typically. Like we deploy far less features than we build, as you would expect. And it's very frustrating to get those features into production, and it can take a long time, and sometimes it could just never happen, which we've seen before. Like, oh, this feature is amazing, makes our model this much better, but it's actually infeasible for us to get that into production because it's just too complicated to process it or to get it at the latency level we need. So I want to highlight things based on what I talked about that aren't the problem, that people sometimes think is the problem. One is that Redis, Spark, etc., isn't good enough. Maybe you have that problem, but it's a typically much more like there are ways to solve it. Like if you're using Dynamo and it's too slow, like try Redis. If you're using Postgres and it's too slow, try Snowflake. Like there are ways to handle those problems, and I won't go into them because they're quite well defined. Another thing that sometimes people talk about is, oh yeah, like we need everything to be streaming. Everything needs to be real time. And it is strictly more complicated to deal with streaming data. Now, again, there is times where that trade-off totally makes sense. But the idea that, oh, we should just write everything as streaming is theoretically super interesting. And you could theoretically say with certainty that a batch is actually a subset of streaming. Like in theory, the streaming problem is a superset of batch. So every batch job can be written as a streaming job. In practice, it's very different. And all the complexity of streaming, you just don't want to think about unless you have to think about it. The other thing that's not a problem, which a lot of feature stores do, a lot of feature stores call them glorified, like we call them literal feature stores. Like literally all they do is store features. Like SageMaker kind of does this. All you're doing in SageMaker is just putting your features there. That's great. It does solve some problems, but everything I've talked about has more to do with like, how do I build and transform the features, unless where do I put it once I've done that? So if you're only just like being a place to store features, you're not solving in my, like what all the things we just talked about in this talk so far. So that's why we built Featureform. We invented this idea called the virtual feature stores, an architecture that we invented. The idea of Featureform was to always build Terraform for features. Terraform for features. The idea is to allow you to define, manage, and serve features for both training and inference. So it's unifying, it's removing that fence, unifying the experimentation phase and the production phase. It runs and stores your features on your infrastructure. So we're not trying to be a new type of database or new infrastructure company. We're much more like a metadata store and an orchestrator. We also are unique in that we provide one pane against streaming, batch, and request time features. Most feature stores only do, either they don't do any of them, it's just like a store for features, or sometimes they might do streaming and batch, but the request time features are dropped. And finally, I didn't really get into what point in time correct training sets mean. That might not mean anything to you. But if you're working with time series data and building models, you've definitely faced the issue of how do I get historical feature values. So Featureform will do that automatically based on your transformations. At any point in time, I probably should have started with this. Feel free to throw questions in the Q&A. Maybe I'll actually give a moment. If anyone has any questions, I'll wait like a minute before I keep going. The next thing I'm going to talk about is how funnily similar and how many parallels there are in the LLM and RAG space as there is in traditional machine learning. So I'll get into that next, but I'll give a moment for questions if there are any. Feel free actually to keep writing your questions. I will take a pause, but I'm going to keep going just to make sure I get through all the content we have. But please drop your questions. And if you're in Zoom, in the webinar, in the Q&A, and if you're in one of the places we're streaming, you should be able to just leave it there. And I think Shab is keeping an eye on everything. Okay, so perhaps you've heard of this thing called GPT. It's it's kind of all the rage right now. Maybe you've even heard of the idea of RAG. RAG is a system, it's an architecture of how to build an application using the LLM on your own private data. RAG stands for Retrieval Augmented Generation. This overly complex image is a example of what RAG looks like. So I did get a question. I'm going to answer it because it's a really good one. The question is, should we save the target column in the feature store or not? It looks like not, but then how do I pull it while training the model? So our take is that the target column or the label column is what we call it, is should be in the feature store. But that is, I believe it's entirely unique to Featureform that we actually handle that. And the reason we do that is we think of a training set as a target column zipped together with n feature columns. Yeah, so that's how we think of that problem, is it's the target with the features, and in that situation, the label column is actually defined in Featureform as well as the training set. Other feature stores don't do that. You actually have to loop through your target column somewhere else and then join them to the features. But I don't think that makes sense, because it just, why would that not be in the feature store? Like that, in my opinion, that should be part of the process. In the examples I'll give, the code examples, I'll actually be able to show you how we do that. But thank you for the question. It's a really good question. Okay, so yeah, going back to LLMs, this is RAG. I'm going to break it down. The idea of RAG is, so products like LLMs take a prompt. And by default, right, if you open ChatGPT and ask, how should I be investing? It's going to give you a pretty decent but very generic answer. If you are a company like a bank and you are building a chatbot, you have a lot of relevant context about that user that you probably want to give the LLM to allow it to give a better response. For example, you might have a set of analytical features like age, how much money they have, how much they spend a month, what they're spending on, etc. So those are in the feature store, funny enough. So it's actually a very similar problem to what we just talked about. The other piece of it is typically like the LLM learns from every piece of, every document more or less that it's allowed to, which means it has a really good holistic generic view of the world. Now, if you're a bank, you might have some specific take, right? It might be slightly like you lean in one direction, like, no, we think you should be investing in this way, even though it's a little more risky or a little more conservative than the average. So you might want to retrieve paragraphs and documents from your own text to prompt the thing. This will all feed together, and it will fit into a prompt structure like below. So that's what RAG is. RAG is that retrieval augmented, retrieving data that's relevant, retrieving context, and augmenting the prompt with that context. So like in the bottom, what we end up with is, given the user has these attributes and using this content from our blog post, answer the question X. So you're taking the user's question, but then you're actually fitting it into a structure that has more information. And the way to do that is in this. I'm going to break it down. There's per request. You're going to want to grab the user ID. You're going to want to grab the user's question. You're going to want to use that information to retrieve the correct context to feed into the prompt. Some of the context can be pre-processed. And especially if you're using something like a vector database, you kind of have to pre-process your documents to feed into the vector DB. This all fits together in almost exactly the same way as what I just talked about. There's 3 types of features. There's pre-processed features that can either be done in batch or streaming. And then there's on-demand features. And the on-demand features in this case would be actually fitting it into the prompt and other things. So when people use Featureform for LLM use cases, the prompt construction happens in the on-demand feature. And then the building and filling in the vector database and the key value database is happening in the other side. So we support vector DB as an inference store. Okay, that was a quick aside. I just it's relevant enough, and I guess it's a big enough topic right now. I want to make sure I touched on it. So let's get back to traditional features. Let's talk about the feature workflow. So I've talked a lot about getting your features into production. Now, chances are you have features in production right now if you're listening to this. I would fathom to guess that this may look familiar. Maybe stuff like this too. The feature engineering process is not only kind of made painful via the fact that you have to have a training pipeline and production pipeline. Just the whole process in general on both sides is pretty ad hoc. There's no orchestration, there's no metadata, like the idea of like what even is a feature. It's like a column in 5 different databases. It's not really well defined. What's missing is a framework for feature orchestration, feature definitions, feature monitoring, management, etc. And that's what Featureform is. So Featureform is a framework, it's a Python framework that sits in a place where your data scientist or you as a data scientist can write SQL, can write Python, can write PySpark in our framework. And it's still the same transformation code, like all the logic is the same, but you're just kind of fitting it into a function based on like our format or our framework. And then Featureform will actually orchestrate it for you on your infrastructure, whether it's AWS, whether it's Azure, whether it's on-prem, whether it's Spark, Snowflake, whatever. A little more in depth, the components of Featureform, there's a repository of definitions. Those are transformations, those are the features, the target columns are the labels, the providers, the training sets. There's a search and discovery component around more around collaboration. So for collaboration, we have things like versioning, lineage, sharing, search, governance and access controls in our enterprise product, which may or may not be relevant to you, monitoring both for uptime and also for data drift and concept drift. And finally, for serving, like we have a serving API both for inference and for training, and you're serving out of the same place so that you don't have to worry about maintaining 2 separate pipelines, because we will kind of join those together. Another thing that's unique to Featureform is we're a virtual feature store. So we take that application layer and we fit it on, you can kind of plug in your infrastructure into it. So we're orchestrating your infrastructure, whether you're using Pandas directly or using Spark or using Snowflake, doesn't really matter. As well as the inference store, again, Redis, Cassandra, Dynamo, we support that and much, much more. Okay. I'm going to show you some code. So I'm going to stop sharing. Again, if you have questions, please leave in the Q&A or the Zoom. If you're in this, or wherever, not the Zoom, but the LinkedIn stream or whatever, wherever you are listening. Oh, I should actually share my slides for a little longer because there's one piece I need to share. So for context, I'm going to show a little bit around fraud detection, or the example is going to be some code from fraud detection model. Fraud detection is a really common use case for feature stores because 1, it's an interactive model. 2, it's very feature heavy. Like typically to make your feature model or fraud detection model better, you're going to be doing a lot of feature engineering. And 3 is there's almost always some aspect of streaming data or features that need to be very fresh. 2, deploying Featureform. I'm not going to show you how to deploy it in this just given time, but it's pretty straightforward. We can deploy it with a Terraform script or a Helm chart, or just we have a single Docker container instance you can run, and you can also actually just run it locally. We're having a workshop rather next week, and in the workshop, I will actually go through a whole frame, like building something end to end with Featureform using local mode. But yeah, Featureform open source natively just runs in Kubernetes. So all this for Terraform and Helm for production deployments, it just runs in Kubernetes. In this example I'm about to show you, we'll build one of each of these kinds of features. So I'm gonna make sure I'm sharing. Yeah, oh cool, it worked. Okay. So 3 types of features. I'm gonna zoom in because I know this is probably a little small for you all. Cool. I'm gonna skip this. I'm gonna get to the client. So Featureform will have been deployed. You'll create a client to Featureform. You will register your infrastructure. So again, Featureform has a plugin infra or plugin architecture. So you can plug in Redis, you can plug in Snowflake, you can plug in whatever. Doesn't matter. You can define your data sets or register your data sets. So you might have like a table. These are like the primary data sets. Like what's the data you're starting to work with? You can then register transformations. So we support both data frames and SQL. So we support both data. I'm going to come. I see there's a question. I'm going to definitely get back to it in a moment. So there's SQL and data frames. You can do either. This is a batch feature. You can actually set this up on the schedule as well. Notice that lots of the logic is almost exactly the same. So you're defining a transformation, and that transformation is going to get run on schedule. This would be the batch example I talked about. Once you build the data sets that you need, you can start to specify which columns are your primary key, which are your entity ID, which columns are your values. You can add the type. If you're going to serve it for inference, you need to set up the inference store, so you can specify where Featureform should send it. We support versioning, so you can specify version. You can also register a stream. And in the stream, you'd register the inference store, you'd register the offline store. So the way a stream works in Featureform is when you write to a stream, it will save it the most recent value into the inference store, and it will also save a historical or like a log of values in the offline store. And what this allows for is that we would know what the feature values were at different points in time, which allows us to what's the word? It allows us to build a point in time correct training set. So someone asked earlier about how about target columns. So this is like a label or a target column, which would be the column that you are going to try to predict. And I'll show how we'll use a feature and a label to build the training set in a moment. The final type of feature is the on-demand feature. And on-demand features are defined like this. It's its own function. And this is just Python. It's just a Python function. You can give it parameters at the request time and do all that, but this is kind of how it works. Finally, you would register a training set. So the training set is a label and a set of features. What Featureform will do is it will kind of loop through that label, and it will join the features to the label at the point in time of the label. So if the label has a timestamp attached, we'll get the features as they would have appeared at that point in time. Great. Then you apply it. And when you apply it, Featureform will actually orchestrate all of that infrastructure to build everything I just declaratively defined. If we were going to change any of these definitions and reapply, Featureform will do the minimum changes to make all that stuff happen. Once we do that, we can, one, for training, I can get the training set by name, and I can just get it as a data frame. I can also loop through it as mini batches, but I can just use it now. And I don't have to worry about, oh, is it a Parquet file? Where's the Parquet file? I have to Spark submit a job or write some Airflow thing. Like it's all just, I define all my stuff and it just happens for me when I apply. For features for inference, you use the features API. In the features API, you would specify either by name or just by reference, you would specify the features you want. If there are request time parameters, you can include those. And then for our entities, which are kind of like, again, like the primary keys, like features and are associated with an entity because they describe something. Like average transactions and last transaction describes a user. So you can specify which user this is for. This will go and do the lookup. So on the entity side, like the average transaction, last transaction, one is a stream and one is batch, but they're both pre-processed. So we'll do a lookup on the inference store. And then USD price is on demand. So what USD price will do is actually pull the function and run it on the client so that you will kind of process this at that moment. And when you run it, you would get your features. So that was quick. I can come back and talk about any of it. I'm going to take a moment to answer questions. I know there's a question waiting, so I'll do that first. So the question is, we can use the feature store for model monitoring also, right? Like use validation data of our model as a reference data and batch inference data as current data and compute drift. So drift is also one of those things that means a million things depending on who you ask. The typical way I think of drift, like the type of drift that tends to exist with relation to models that is very unique to machine learning is you train your model. You have some set of features. Those features have some statistical properties, like a distribution. When the model is deployed, it's assuming to an extent that the data it will continue to see will sort of match that distribution for each of those features. In practice, that doesn't always happen. In practice, like the distributions change. Now, certain models should be good enough at this that they're maybe unaffected by the drift change. If they generalize really well, like even like small changes in feature distribution shouldn't have an effect. But sometimes it does. And being able to proactively see what features are drifting and how things are changing, and essentially like it's a dynamic environment and understanding what is changing. And so you can kind of try to proactively catch things before your model starts misbehaving is really important. So the way you think of it is like, if I have a feature X, you calculate all these statistical properties of it in the training data, and then you maintain all of those statistics with every single inference, and you compare. And if the statistical similarity between those two data sets is similar, then you're fine. If they change past some sort of certain heuristic, then you would say they drifted. So that's how I think of what drift means in this context. So it's like compare your distributions in your training data to distributions that you're actually observing in production. Great question. Any other questions? Anything else I can highlight with the API or the code? I know I kind of went through a lot of it quickly. Give a few more minutes if there's any questions. Otherwise, actually, we can wrap up. I don't actually have much other content. Cool. Give a few more minutes. And Shab, are we checking LinkedIn and I know we're also streaming, but as well for questions?
Yes, we're checking LinkedIn, YouTube, and Twitter.
Nice. Awesome. So feel free to, if you're writing up a question, feel free to keep writing it out. I'll answer it. Soon I'm going to plug that we have a workshop next week, which will be really cool. If you want to get very hands-on with Featureform, it's a great place to do so. We also have a community, a Slack community that you can join. Featureform is open source. So everything I showed here, except streaming, is open source. So you can actually go and just get the repo and play around with it. And yeah, cool. I'll give this one more minute if there's any final lingering questions. Otherwise, we'll call it for today. So sharing my screen. So I'm gonna make you host. And if you have any questions, speak now or forever hold your peace. You can just email me also or ask in Slack. But for today, I think we're good. Shaba made you host, so you should be able to end everything.
Okay, cool. Yeah, I will be sending out a follow-up email to all of our attendees with a link to the recording, a link to our community, and our workshop next week. Thank you all for coming.